My name is Ian Youmans.
This is Bryson Schmitt.
I'm Michael.
I'm Josh Moseley, and this is Group 6.
The goal of this project is to use standalone systems to measure different data in the common environment. Each lesson will require a measurement of distance or temperature. We are looking to find the distance of an object in a room, the depth of water, as well as the temperature of a room or of an object. To find the answers, we will be coding an Arduino board to acquire and display proper measurement data. We will be using components included with the Arduino kit. The components we will be using are the Uno R3 board, male-to-male wires, female-to-male wires, servo motor, water level detection sensor, ultrasonic sensor, LCD module, 10 ohm resistor, thermistor, potentiometer, and a breadboard. Each lesson will use different code with a combination of different components to receive an accurate output measurement. The strategy to achieve the project goals will be to use basic measurement tools to check our work. This will ensure that our code and component setup is working properly. It is also important to check the range of each desired measurement to ensure they are within the range that the components can detect. Device calibration is also important to receive accurate results. When conducting the experiments, rulers and thermometers will be used to ensure precision and accuracy. When measuring length and water depth, for example, the ruler will be used to compare real numbers with readout data from the Arduino kit. If the two results are not comparable, we will make changes to the code and components. The experiment can then be repeated until the correct data is acquired.
We connected our USB port, downloaded and installed the correct driver on the computer, and then we used the code to run the servo with the double-sided top.
So here we have a depth measurement device and a servo motor connected. Depth measurement device, this goes to pin. They have the pins going to A0 ground and then 5 volts. The servo, it goes to 3.3 volts, 9, pin 9, and then ground. Here we have the code that depending on, the servo motor will go to a different degree position depending on what range of values it in. And it's also converts into millimeters. So here we have it actually going into the water. You can see the millimeters on the left and the ADC value on the right. And the servo will go to different position depending on total depth it goes under. For calibration, a ruler was used and we set it up beside it when dunking it into the water to see what depth it was at. We have a here we hooked up a servo motor, an ultrasonic sensor. So we have some of the wires going to pins 11 and 12, and then we have these going, one of them going to ground in 5 volts. The other we have the servo motor. One is connected to pin 9, and one is to ground and 3.3 volts. So you can see here we have the serial monitor up, and it converts the distance calculated by the ultrasonic sensor into a the degree position for the servo motor. And so for the calibration of this, I took a ruler, I put this parallel to here as close as possible, right at the 0 mark. Then I position a solid object such as this at varying degrees of distances, and you can see the result there on the serial monitor.
We're able to replicate the diagram onto our unit here with relative ease. The main problem we ran into was after uploading our code, the LCD readout was reporting a bunch of gibberish, as seen here. After consulting various forums and troubleshooting help, we came to the realization that one of our wires was probably bad, so we replaced the entire batch, which is found here, with an entirely new batch, and now our readout is working just fine. For calibration, we applied a heat source to the Accurate thermometer shown here, as well as the same heat source to our thermistor here. We allowed both instruments to reach a relatively similar temperature, around 31 degrees, and then after both stabilized, we released, and allowed both instruments to respond accordingly, and we tracked the trends. What we learned from this experiment was that since we are measuring two output values for the same input value, we are going to incur a hysteresis error. A scenario where this application can be used is in assessing the performance or error in performance of a typical pressure transducer, primarily assessing the error of hysteresis and thermal sensitivity.
The goal of this experiment was to use standalone electronic systems to quantify basic measurements in common environments. The significance of this project was that we calibrated these electronic systems to basic, consistently accurate measuring tools to test the accuracy of the systems and use hysteresis and zero-shift principles to measure the error in the systems compared to their basic counterparts, aka rulers and thermometers. In the field of engineering, these principles are important as there are countless occasions where using a ruler or thermometer just won't be practical. But we use more common scenarios to calibrate complex measuring systems like depth and distance sensors so that they can accurately quantify much larger, more significant measurements like the distance of two buildings or the depth of a large body of water.